Thank you very much for the introduction, and thank you all for joining. Today, I will present the main topics and findings of my PhD, which focuses on emerging resistive memories in the RF domain and their use for adaptive RF transceivers. This research was done under the supervision of Professor Eilami Alon and Professor Shahar Kpatinsky at the Andrew and Erna Viterbi Faculty of Electrical Engineering at the Technion. We have all been witnesses of the exponential expansion of wireless communications, from smartphones to wearables, IoT, and mobile healthcare. It has been predicted that by 2025, there will be approximately 80 billion mobile devices connected to the internet, further increasing the heterogeneity of radio frequency standards in the wireless communication ecosystem. It's not surprising then that the number of wireless standards has also increased exponentially to support the various functionalities, data rates, and coverage distances required for the new applications. Without any doubt, the main driver of the revolution of wireless communication has been the smartphone. As you can see in this teardown of an iPhone 10, much of the area of just one side of the main board is dedicated to RF transceivers, which must provide support for different standards, frequency bands, and data rates. The smartphone must support also the new standards like 5G and in the future 6G, together with the requirement of backward compatibility. Clearly, this solution is not scalable without improved integration and miniaturization. So the question is then how to maintain the miniaturization trend, low power consumption, and high performance as the number of standards continues to increase. And the answer is through reconfigurable radios or adaptive radios that can support multiple frequency bands and the coexistence of several wireless communication standards with what we call a multi-standard radio. Adaptive RF integrated circuits or RFICs reduce the need for independent RF chains for each band, thus enabling for block reutilization, eliminating redundant components, adding flexibility, reducing area and complexity of wireless front ends, which in turn reduces the time to market and development cost of radio transceivers. There are two ways of providing reconfigurability. The first one is inter-circuit reconfiguration, where the connection between the different blocks of the RF chain, that is the antenna, filters, amplifiers, and so on, can be changed and reconfigured through the different applications and standards. And the other type of reconfigurability is the intra-circuit reconfiguration, where some parameter of the block, such as the resonant frequency, can be changed. In both methods, the fundamental element is the RF switch. RF switches are fundamental components in radio transceivers for the control of the signal flow and to multiplex the access to shared resources or blocks. When on, it allows for the flow of the RF signal, and while off, it prevents the flow of the RF signal. In a first order, the RF switch can be modeled as a parallel RC circuit, where the on state is the on state performance, which is measured by the insertion loss, is mainly determined by the on resistance. Because low on resistance is required, then these devices usually have a large footprint. And the off-state performance, where it's measured by the isolation, is determined by the parasitic capacitance, or C off. Then the on-state resistance and off capacitance determine one of the main figures of merits of the switches, which is the cutoff frequency. Other aspects that are important in RF switches are linearity, power handling, switching time, endurance, and switching energy. The current standard RF technologies include the silicon on insulator FET or SOI FET, the microelectromechanical systems or RF MEMS, and 3,5 compound transistors as the PHEMT or pseudomorphic HEMT. The SOI FET can be used as a fast RF switch by controlling the gate voltage, which changes the resistance of the channel, and it's preferred to bulk CMOS due to its reduced parasitic capacitance provided by the buried oxide or box. However, in these devices, there's still a tight trade-off between the on resistance and the off capacitance. As we know, increasing the width of the transistor reduces the on resistance, but at the same time increases the off capacitance respectively. Therefore, the area requirement of these devices can be hundreds of micrometers square. The RF MEMS rely on a mechanical movement of a cantilever that switches an ohmic or capacitive contact, which is electrostatically controlled. They achieve excellent RF performance with low power consumption, but require large footprints. They have slow switching speeds and require non-standard fabrication process, which also increases the cost of these devices. Finally, the 3-5 compounds, like the pseudomorphic high electron mobility transistors, have very good RF performance, excellent RF performance, but have the disadvantages that they are normally on devices. They require quite large area for low on resistance, and they require also non-standard process, which is still expensive and inefficient. Recently, resistive memory technologies, or simply memristor technologies, such as resistive random access memory or ReRAM, conductive bridge RAM or CVRAM, and phase change memory PCM, have emerged as great candidates for RF switches due to their superb transmission properties, the smooth footprint, their non-volatility, and back-end of the line compatibility, as they can be built between the metal layers. These devices share the characteristic that the state is stored as a resistance, and particularly resistive RAM is based on defects in the thin metal oxide layer, which is called oxygen vacancies, which can be modulated to form a metallic filament, which will change the conductivity of the insulating layer. CVRAM, in turn, relies on redox reactions in the active electrode, which provides with ions that migrate along the electric field to the inert electrode, where they are reduced, forming a metallic filament, which also changes the conductance between the bottom and top electrodes. Finally, PCM relies on the large conductivity contrast between the crystalline and amorphous phase of chalcogenide phase change materials. Several switches based on these technologies have been proposed, which achieve low on resistance and low capacitance, therefore achieving state-of-the-art cutoff frequency, which is the figures of merit of RF switches, and therefore making them great candidates and great contenders to the best-in-class RF switches, which are the FETs, PHEMs, and MEMS. Particularly, the 4-terminal PCM device stands out due to its built-in DC and RF decoupling, as the actuation path and the RF path are independent from each other. Some semiconductor companies, such as Tower, have already started looking on these technologies for commercial purposes, and this technology particularly I will expand on later. So let's see how these memristive technologies, PCM, ReRAM, and CVRAM do when compared to standard RF switches. We can see that PCM has an excellent field of merit with medium endurance and low actuation voltage and medium-high switching power. Resistive RAM presents a significantly lower field of merit, but smaller area compared to PCM, lower actuation voltages, and low switching power. CVRAM in turn has an excellent field of merit, but reduced endurance compared to the other memristive technologies. But obviously, all these memristive technologies don't consume idle power since they are non-volatile switches. FETs have a higher endurance and certainly CMOS compatible actuation voltages because they're CMOS devices, but with large area and limited field of merit. Finally, MEMS provide very high field of merit, but require very large actuation voltages and large area. So following this comparison, it's clear that memristive devices are great candidates for RF applications due to their high performance, non-volatility, back-end of the line compatibility, and reduced footprint. Therefore, they can provide adaptability to RFIC, and they can be the key technology that will enable massive reconfigurable RFICs. The aim of my research was to explore memristive devices in high-frequency applications in several abstraction levels, from device to circuits and systems. At the device level, I worked on the development and fabrication of 4-terminal phased RF switches at the Technion facilities, and on the characterization and modeling of memristive RF switches. I proposed several compact models to accurately predict their behavior, both the dynamic behavior and RF behavior. Furthermore, I've explored the novel characteristic of these devices to provide tunability to different back-end of the line devices like inductors and capacitors, and also for multiplexing. And finally, how to use all these devices to improve the adaptability of RF blocks such as low noise amplifiers. In the rest of my talk, I will introduce my work on the development of indirectly heated phase change RF switches, or IPCS. Then I will present in a nutshell how different aspects of electro-thermal and RF modeling of memristive RF switches. I will then present how to use the IPCS as a platform for nanosecond probing of chalcogenides and other materials, allowing to perform electro-thermal characterization up to 1000 Kelvin. And finally, I will present some of the reconfigurable RF circuits based on memristive technologies that I proposed during my PhD. So phase change materials are the active material and the fundamental material in the IPCS, or again, the indirectly heated inline phase change switch. PCM chalcogenides are compounds of the trinary of germanium, antimony, and tellurium, which present a large resistivity contrast between the amorphous and crystalline phases. These materials are not new and have been used in the past for rewritable CDs and DVDs. They are currently being used for non-volatile non-volatile memories such as Intel Optane for persistent memory and storage class memory. And it has been foreseen that in the future they will be used for RF, millimeter wave, and optoelectronics applications. The phase transition in these materials is thermally activated. Suppose that initially the PCM is in its crystalline phase or low resistive state. And to amorphize the PCM, a large current or amplitude or a large current or voltage pulse is applied so that the temperature will rise beyond the melting point, the melting temperature, and the fast quenching or cooling process will freeze the atoms in a disordered amorphous manner. Conversely, a mild amplitude pulse will anneal and crystallize the PCM back to its crystalline phase. Hence, the process is reversible. The 4-terminal indirectly heated phase change switches, IPCS, has been proposed for high-performance RF applications thanks to their state-of-the-art performance, or state-of-the-art cutoff frequency. Based on previous work by El Hinawi and others, I developed the fabrication process of these devices at the Technion facilities, which allow us to be one of the few universities around the world that have access to this process. The IPCS consists of 2 RF ports in line with the PCM, as you can see here, separated by a very small gap, and 2 terminals for the thermal actuation, as you can see here, top and bottom, using an embedded heater. Okay. This heater runs transversely to the direction of the RF path under the PCM. The heater and the PCM are separated by a thin electrically isolating film, the dielectric 2 here, that it's usually silicon nitride, and therefore there's a built-in RF DC decoupling. So far, the germanium telluride has been the material of choice for RF applications due to its low resistivity in the crystalline phase and relatively large resistivity contrast with the amorphous state. Here you can see some CEM top view of our devices and a field cross-section of the fabricated devices. You can see the different layers and how the heater and the PCM are isolated by a thin electrically isolating layer. So let's see how the IPCS works. When the PCM is in the crystalline phase, the RF signal flows between the RF ports. Meanwhile, when the PCM is in the amorphous phase, the signal is reflected back from the input port. The device, as I mentioned, is thermally actuated with voltage or current pulses at the heater. During programming, heat is conducted through the dielectric tube up to the PCM layer, and then it's dissipated through the contacts and substrate through dielectric 2 and dielectric 1. And certainly, during the actuation, some of the heat is dissipated through the dielectric 1, 2, and the contacts. Therefore, proper engineering of the different layers is required to achieve switching at all and low switching power. Recall that the cooling must be fast. We need a fast quenching process, so the dielectric 1 must be kept as thin as possible. And also, the more the contacts are overlapped to the heater here, the larger the energy dissipation will be. This poses a very interesting thermoelectric trade-off between the thickness of the different layers. Other design trade-off in the distance of is the distance between the electrodes. A smaller gap between the two electrodes will reduce the on resistance, as you can see here, but will increase the off capacitance. Also, the smaller gap will increase the heat spreading through the RF contacts, and therefore will increase the switching power, as you can see here. So the thickness of the PCM is also will also affect the RF performance, of course, because a thicker PCM layer will reduce the sheet resistance. On the other hand, we will need more power to switch the phase of these materials. During the process development, of course, we encountered with several challenges, including how to fabricate contacts with low contact resistance between the phase change material and the metals. This was because the germanium telluride oxidizes fast in ambient conditions. So we needed to develop a surface treatment procedure to remove germanium oxide between the contacts are deposited. Also, another problem is the steep topographic change at the heater area, as you can see here, which generates voids at the edge of the heater. Due to the lack of a planarization process, our solution was to have overlap contacts over the heater area. Other issues encountered were the oxidation of the PCM while programming, addition problems of the germanium telluride over the silicon nitride, as you can see here, and reliability issues of the heater due to the high currents, high current densities that are required for programming, which caused, of course, electromigration. Fortunately, we managed to overcome these issues, and working devices with state-of-the-art cutoff frequency were fabricated. To enumerate some of the advantages of this device, I want to highlight the high cutoff frequency, very close to the state-of-the-art, non-volatility, which means that there's no energy consumption while the switch is idle, just power consumption when switching the device. The middle-low switching energy compared to other devices, very small footprint. You can see here it's 40 micrometers squared. It might seem large, but believe me, when talking about the transistors, as I mentioned before, to achieve low on resistance, we need hundreds of micrometers squared. So this is a small footprint. And also it's back end of the line compatibility. These devices, this process can be adapted very easily to standard fabrication processes. But of course, there are some limitations as the power handling, switching time, and endurance. The power handling particularly is limited by the threshold voltage or Ovchinsky threshold switching phenomena, which can trigger an unintentional phase transition when the RF signal surpasses a certain power level. I will expand on this issue later on, so don't worry. The switching time is limited by the crystallization time, and it's usually something around 1 microsecond. And we are currently working on a method to improve this transition time by 5 to 10 times. The best endurance achieved so far has been 10 million cycles achieved by HRL's group. but it could be improved with more research on material engineering, on the PCM and the heater. Of course, the endurance in our devices is still pretty low compared to that numbers, but it's still a working device. We have seen the IPCS, the inductive heated phase change RF switches, and now we will move forward to characterization and modeling of the IPCS and other resistive RF switches. One of the main challenges when developing the IPCS fabrication process was lack of a computer-efficient model that could rapidly predict the dynamic behavior, both thermal and at high frequency in a circuit environment. Hence, we took this challenge and developed a compact model of the IPCS, and our model accurately describes the electro-thermal and RF behavior of the switch. There's a behavioral model that controls the resistance state, which changes as a function of the PCM temperature. And then the PCM temperature is estimated by an RC thermal equivalent model, where each layer is modeled by the thermal resistance and thermal capacitance, being the heater, the heat source. Then, as we can see here, the different layers, this will be the electric 2 silicon nitride layer, modeled by our thermal resistance and thermal capacitance, the thermal resistance capacitance of the PCM, and the capping layer. And to the bottom, you will see the thermal capacitance and resistance of the electric 1, which is silicon oxide, and the substrate. And this model has also an RF model included, which predicts the parasitic capacitance between the RF electrodes, the parasitic capacitance between the RF electrodes and the heaters, and as well as the fringe capacitance between the RF path and the heater path. The whole model was implemented in Verilog 8, and it's freely available at nanohub.org. Furthermore, we presented for the first time electrical thermometry of operating IPCS devices. These measurements were used to calibrate the model, and as you can see here, as temperature rises, temperature of the heater rises, its resistance changes accordingly to the temperature coefficient of resistance, or TCR, of the heater material. This in turn changes the voltage drop at the heater. So by measuring the voltage variation at the heater, the resistance change can be determined, and then it can be converted to delta T using the TCR of the tungsten of the heater. Our model accurately predicts the temperature variation of the heater, as you can see here in the right panel, and the black solid lines. Hence predicting the heater voltage as in the left panel, and the resistance variation of the heater within a 10% error. Note that in the right panel, the model predicts also the cooling time, which cannot be determined by this measurement setup, since the falling time of the voltage pulse is much faster than the thermal time constant. So a different method that I will show later on allow us to properly characterize this quenching time also. The electrical thermometry setup that we built doesn't provide us accurate information about the PCM temperature variation. Therefore, we model the IPCS also in COMSOL multiphysics as a finite element model, where we can see in the right figure that the compact model, that is the solid line, and the finite element method simulations, that are the dots, agree. Okay, it can be appreciated also that increasing the pulse width is between 100 nanoseconds and 200 nanoseconds reduces the reset power. There's more time to achieve the steady state temperature. The model can be, as I mentioned, the model also accurately predicts the RF performance of the IPCS. So as you can see here in the two panels, you can see in the left panel the insertion loss and the isolation of a 20 micron device. While in the right panel, you can observe the isolation for a 20 micron and 40 micron devices. The solid lines are the model performance, and the dots, triangles, are the experimental measurements on the device. Also, see that the insertion loss, it's very low. It's below half dB, and the insertion loss and the isolation, sorry, it's beyond 25 dB for this frequency band up to 10 gigahertz. It's obvious, but I was worth mentioning, increasing the width of the RF contacts will improve the insertion loss, but at the same time will reduce the isolation, as you can see in the right panel. The main advantage of this model, in conclusion, is that this model allows for co-optimization design of the switch and to achieve high RF performance and low power. An important conclusion of this work is that for the case where the heater width and the RF gap are equal, scaling improves both the RF performance. You can see here in the left axis the cutoff frequency, that's the figure of merit in terms of RF performance, and will also improve the switching power, which is determined by the minimum power for amorphization, that is the MPA. So during my PhD, I have also worked on device modeling of also CVRAM and and ReRAM RF switches. And here you can see our LAMP model for a CVRAM RF switch. This work is from the University of Massachusetts in Amherst, and we received experimental measurements of this device and built our model around it. This physics-based model, our physics-based model predicts the dynamic and RF behavior using an analytical model where the circuit parameters of the LAMPed model are determined by the device dimensions. Our model improves the accuracy over previous models, allowing for better circuit design. A similar model was developed for a resistive RAM-based RF switch in collaboration with Professor Gina Adams from George Washington University, where we also, you can see here, achieved very accurate results. So far I introduced the resistive RF switches, particularly our work on the IPCS and modeling of different resistive RF switches. While we were developing the IPCS process and its electro-thermal model, we discovered that the IPCS could become an amazing platform for high-speed probing of different materials. So I will now present the main results of this ongoing work, which are really exciting and promising. As I mentioned before, PCM is a technologically attractive material, which is currently being explored for non-volatile memory, neuromorphic computing, and optoelectronics, and most recently for RF switches. These applications have different requirements. For instance, memory applications require high off-on ratio, high endurance, and fast switching. And meanwhile, the RF switches require foremost very low on resistance. The different requirements and variations of the phase change materials makes even more crucial to understand the fundamental physics and physical properties and limitations of these materials. And as previously discussed, the phase transition chalcogenides is thermally activated, and the kinetics can span orders of magnitude in time from several minutes down to sub-nanosecond timescales. And the temperatures required for the transitions can go up almost or beyond 1000 Kelvin. Generally, the chalcogenides have a crystallization temperature that is around 200 Celsius or 500 Kelvins, and the melting temperature is around 700 Celsius or 1000 Kelvin. And the self-heating in PCM devices require temperatures that go up to the melting temperature, which is something around 1000 Kelvin, and time scales of nanoseconds. The classic way to prove temperature-dependent characteristics is usually the hot stage. The hot stage can provide middle-low temperatures and timescales that are several seconds to minutes. So it's not possible to be on this side. Previous works, as the microthermal stage, achieved middle-high temperatures down to microseconds temporal resolution, but still not down to the nanoseconds that are required for the self-heating, which is for the quench process, or the heating and quench process, that is the amorphization. So there's still a need for a platform that can properly probe the thermal actuation with nanosecond temporal resolution and heating capabilities up to the melting temperature. So in this work, we used the IPCS not as an RF switch. I want to emphasize that, not as an RF switch, but as a platform for nanosecond probing of the PCM and other materials in the future. This is due to the intrinsic decoupling that exists between the actuation path and the PCM because of the isolation layer. Okay, so the IPCS can prove, with the IPCS we can prove also the melt quench process, which was not possible with previous works. And this platform can help us understand the fundamental material properties of PCMs, particularly physics of melt quench process in nanoscale devices. We can also use it for interface versus bulk effects measurements, drift, and threshold voltage phenomena characterization. Our setup allows for the first time to prove simultaneously the phase transition while the actuation pulse is applied. In our setup, we connect the heater in parallel with the scope in high impedance, and the PCM path is in series with the scope to prove simultaneously both paths. By applying 2 pulses, as we've shown here, we can prove simultaneously the resistance of the PCM and the heater. The resistance variation of the heater, as I mentioned before, allow us to calculate the temperature variation on the device, while the resistance of the PCM allow us to probe the phase transition properties, such as the crystallization and quenching time, resistivities, etc. So with the proposed setup, for the first time, we can probe crystallization and amorphization transitions simultaneously with the actuation pulse. On the left panel, you can see the crystallization process, where the left axis is the delta T of the heater, and the right axis is the resistance of the PCM. When the temperature rises above the crystallization point, it triggers a crystallization process, reducing the resistance. Hence, with this scheme, we can easily determine the crystallization temperature. Contrarily, as you can see in the right panel, when the temperature rises above the melting point here, you can see that the resistance reduces to the melt resistance that is smaller even than the crystalline resistance, and then a fast quench process is triggered, amorphizing the PCM and achieving a higher resistance state. Also, to prove that the input about the melt resistance being smaller than the crystalline phase, we use a reset pulse, use it to prove the melt resistance starting from the high resistance state. So we start at the amorphous resistance, high resistance state. As the temperature rises, the resistance decreases down to the melting resistance, and compared to the crystalline resistance, this is lower. And then when the pulse ends, the quenching process or the cooling process is triggered, returning the phase into the high resistance state. This way we can also characterize the quenching time of these devices. This effect can also be observed in the right graph, which shows the power density in the heater versus the current of the PCM. As the PCM achieves the melting temperature, the resistance is reduced, and then the quench process begins, reducing once again the resistance. So here you can see again how the current rises when the device achieves or goes beyond the melting temperature. So let's now move forward and see how these devices can be used for adaptive RF circuits. Let's start with the non-volatile single pole double throw or SPDT switches, which are multiplexers in the RF domains. These are fundamental blocks for adaptive RFIC because they can provide and control the access to shared resources such as antennas and other blocks in the RF chain. We propose several topologies of the SPDT using CBRAM RF switches, and these devices improve basically the transmission performance with lower area overhead and lower power consumption. In one of the advantage of the series and shunt topologies with the CBRAM switches is that both branches can be programmed with a single control signal. Okay, this is because this is a two-terminal device. But of course, that poses a limitation, which is that we need extra circuitry to decouple RF and DC. And of course, this problem of the RF DC decoupling can be solved with the IPCS, which has a built-in DC and RF decoupling. So we have been working on SPDT based on the IPCS also. But before that, I mentioned before that one of the limitations of the IPCS is the power handling compatibilities, which is limited by the threshold switching or Ovchinsky threshold switching phenomena, where the resistance of the PCM in the amorphous phase is suddenly reduced when the voltage exceeds a certain value, that is the threshold voltage. Though this is the phenomenon that allows the PCM to work as a two-terminal memory device, in the IPCS, it can trigger an unintentional phase transition when the RF signal surpasses a certain power level. And since the threshold voltage is determined by the dimensions of the PCM, then in the IPCS, this threshold voltage will usually be much higher than in two-terminal devices, but still it limits the maximum power that we can apply to the switches. And so to overcome this power handling issue, we used a series parallel configuration scheme where two devices are connected in series and in parallel with two other devices. This way, the on resistance and the off capacitance theoretically remain low, almost equal to the single device if we are talking about ideal conditions. But if not in the real world, it will be almost equal to the single device, to the single series device. Also, the voltage drop at each device will be smaller because of the configuration, and therefore we will prevent that the voltage will rise above the threshold voltage, causing an undesired phase transition. So here you can see some preliminary results of a single pole, single throw device. This is a single switch. You can see that the results are pretty promising and exciting, and we expect a power handling that is above 30 dBm. We used this idea to build a single pole double throw, okay, a multiplexer with the series shunt quad configuration. That's how we call it. And this SPDT is intended to be used for as a transmission SPDT for the DC to 6 gigahertz radar applications. And also here we expect a power handling that's larger than 30 dBm. Also, we expect a little bit higher, 36 dBm, but we will see. It's an ongoing work. Also, during my PhD, I explored how to use these switches to provide tunability to other back-end of the line devices, such as inductors. As you know, inductors are built in the top metal layers using spiral loops to exploit the mutual inductance between the wires. And the inner terminal is usually connected using a cross-under metal. Therefore, as in a membristive crossbar array, a membristive switch can be built in the cross junction between the upper layer and the cross-under. This is usually done in the top metal layers because we want a low resistance, and the membristive switch can be built in the cross junction of the two metal layers. This membristive via can be used to change the effective number of turns in the inductor. We will change eventually the inductance of the inductor. This is a very simple but elegant way to tune the inductance, as you will see. When the device is off, the current flows through the whole spiral like in a regular inductor. but when the switch is on, because of its low on resistance, the current will flow mostly through the outer spiral. Okay, and this way we can reconfigure or change the inductance of the inductor. And because the device is built in between the metal layers, there's no need to go down to the front end to the transistors to provide tunability, which causes added parasitics, which will reduce the performance of the tunable inductor. So this topology was simulated using a 3D electromagnetic simulator. Observe how the inductance is changing accordingly to the state of the memristive via switch, and of course it will change the quality factor, that it's the ratio between the inductive part and the resistive part of the inductor, or a metric of how much resistivity there is in the inductor. With this topology, we achieve a tunability ratio, that's the ratio between the maximum and minimum inductance of about 3 or 300, which is a lot compared to other technologies. And it's worth mentioning that we are also working on tunable inductors based on the IPCS and developing the fabrication process of these devices. The tunable inductors was also used in larger circuits to provide tunability, and particularly in this case to a low noise amplifier. The gate and the drain inductors, LG and L out, were implemented with memristive via switches. And this allows us to tune the input and matching network and the output matching network to multiple frequency bands. And in particular, this LNA was designed for the Wi-Fi frequency bands of 2.4 gigahertz and 5 gigahertz. And since the stability is also tightly related to the inductors at the input matching network and the output matching networks, these tunable inductors can allow to improve the stability of these blocks. And once again, because of the non-volatile characteristic and the small area, and the fact that it's built in the back end of the line, we don't have extra area overhead and idle power consumption, which is an advantage over other implementations of dual band low noise amplifiers. So you can see here simulation results that show the potential of this technology for reconfigurable blocks, which is intra-circuit reconfiguration. You can see how the gain represented by the S21 parameter is tuned for both frequencies depending on the state of the inductor or the state of the memristor, and also changes the noise figure, which is an important characteristic in low noise LNAs. And it's worth mentioning that, as you can see here, it's not the same gain, but it's because we didn't use any extra gain boosting technique. So there's still plenty of room for improvement in this work. So that leads me to the conclusions of this talk. In summary, during my PhD, I had the opportunity to explore the novel capabilities of memristive devices in the RF domains, from circuits to devices. I developed the fabrication process of the IPCS at the Technion facilities, which make the Technion one of the few universities in the world to have access to this technology. These devices achieve state-of-the-art performance. And also I proposed the first compact model of the IPCS, which mimics the behavior of both thermal and RF of this device, allowing for fast design and optimization. This work also includes the first electro-thermal measurements of complete and functional devices. I've also developed RF models for zero RAM and resistive RAM RF switches, which achieve better accuracy than previously proposed models. And furthermore, during the development of the IPCS and its model, we discovered that the possibility of using the IPCS structure as a platform for high-speed probing of different chalcogenides. This allows us to perform temperature-dependent characterization up to 1,000 Kelvin with a time constant down to nanoseconds, and we are really excited about this work. Finally, several examples of adaptive RF circuits were demonstrated, including SPDTs, tunable inductors, and dual band LNAs, which we think that will prove that our vision that integrating the membrane RF switches with standard transistor process can open a whole new world of opportunities in the semiconductor industry for dense, low power, multi-standard radios. So I cannot finish this presentation without acknowledging the people that make this work possible. First of all, I want to thank to my advisors, Professor Ilham Yalon and Professor Shachar Patinsky. I will always appreciate what you have done for me and for my career. I want to thank you for believing in me, for the passion and patience during the PhD journey. Of course, this research would have not been possible without your guidance, contributions, continued support, and feedback. And I'm really, really privileged to have been mentored by these two wonderful advisors. I would also like to thank my friends at ASIC Square, Yalon Lav, and the MNFU for the endless discussions, for the assistance, and particularly for the moral support during these 5 years. I would like to particularly thank Guy, Anconina, Arkady, Loai, Keren, Emmanuel, Ami Oren, Nimrod, Balak, Rotem, and Sofnat, who have helped me through all these years. Also would like to thank to the funding agencies that make this research possible, and the RVNI, the Electron Device Society, the IEEE, the Israel Innovation Authority, and the ERC. Also, of course, to the E faculty at the Technion for supporting my PhD studies. And of course, to my family, who's always been present, who has always believed in me and supported me along the way, and particularly to my wife, Nati, and my newborn son, Tommy, for their endless love, patience, and support. And of course, thank you all for joining. Gracias. I will be happy to answer your questions now.
Thank you, Nico. It was great. Questions?
Yes, I have a question.
Yeah, done.
Can you hear me?
Yeah.
Thanks for a great talk, Nico. Wonderful work. I want to ask if you could elaborate a little bit more about how the temperature was measured in the fast crystallization experiment you were showing.
Yeah. Okay, so the idea here is to measure the voltage variation of the, first we characterize the TCR, the temporal coefficient of resistance of the heater using a thermal stage, a chuck. And then with the TCR, we can measure the voltage variation of the heater while applying the pulse. The setup is configured for a 50 ohm network, so the variation beyond or between the 50 ohms can tell us the resistance variation of the heater. With the resistance variation, then we can calculate the delta T using the TCR. So that's about the temperature variation of the heater. With the COMSOL model, we can and the compact model, we can determine the PCM temperature, and that was calibrating using both the COMSOL simulations and the compact model. That allows us to get an indication of what's the temperature at the PCM. And the resistance when probing the phase transition, we have, as you can see here, also another pulse that's simultaneous with the heating pulse, which allows us to check the current variation. Actually, we check the voltage at the scope divided by the 50 ohms of the scope. We have the current on the phase change material path.
Okay, thank you, Nico.
You're welcome.
Nico, can I ask a question? It's Ariel.
Yeah, sure. Hey, Ariel.
Hi. Great talk. Thanks. So just a couple of maybe I missed some of the numbers. So what is the on resistance that you can get at, I don't know, like 10, 20 gigahertz? And what about the off capacitance I would have? I don't know, like you probably have some parasitic capacitance.
Yeah, so the, let me go to this slide, sorry, here. So obviously it depends on the dimension of the device, and depending of what's the application that you want to use, increasing the width of the device will reduce the on resistance. You can get down to 2 ohms with our fabrication process. Others have shown on resistance below 1 ohm. That's because of the limitations that I mentioned on the fabrication process at the Technion facilities. But with these devices, you can get down to 2 ohms with 30 micron width wide devices. The parasitic capacitance there will be a little bit higher, something like 15 femtofarads. And also an issue that it's actually comes from the way that we managed to overcome some of the fabrication process issues was that to have overlap contacts, which limits also the capacitance at high or the performance at very high frequencies. So at up to 15 gigahertz, you will have a pretty good insertion loss and isolation. Beyond that, the parasitic capacitance between the RF contacts and the heater will be dominant and can limit the performance. But it's still a matter of, again, what's the application that you want and what would we like to sacrifice between the insertion loss and the isolation. Still state-of-the-art performance, but there's a trade-off over there.
Thanks. Okay, maybe I'll ask another question later if there's time.
You can ask.
Yeah, seems there is. Yeah. So can you reach also some intermediate states?
Yeah, good, excellent question. That's something that we are currently working on. You can also achieve intermediate states like partial crystallization. It's easier to have partial crystallization rather than partial amorphization, but still we have seen that it's possible to have a multi-states in both directions. And it's a matter of changing the amplitude of the voltage or the pulse width of the voltage pulse.
And they're also stable.
They're also stable, and it can allow to improve. To have some applications like attenuators, tunable attenuators with a single device. Yeah, that's definitely something that we are interested in looking at.
Okay. Thanks.
Any more questions? If not, then Nico, Mazal Tov.
Tada. Thanks everyone for joining.
Okay.
Thank you.
Congrats, Nico.
Bye bye.
Bye, Nico. Great talk.
Thanks.
Congratulations.